Okay, so this time I will speak about how we can use deep learning for inverse design and specifically for nano-photonics inverse design. So what is inverse design actually? So inverse design is basically the rational design of any device in nanophotonics, for example, like nanophotonic structures. For instance, we might want to maximize the scattering of a nanostructure at a specific wavelength or over a broad wavelength range. And what we can do if we have a very simple geometry, then probably it's easiest to just do a systematic analysis of the possible geometric parameters, for instance, the diameter of a disk. And then we just choose manually the diameter or the parameter at which we have the optimum solution. Now, if we have a bit more complex nanostructures, this might be a bit tedious, or the parameter space might be too large to explore it systematically. Then the first method that might come into mind is probably numerical optimization, and we might try to optimize the geometry with normal minimization or maximization algorithms. So there already, if we have a simple problem, we have a first problem probably that might occur, because usually we don't have a single optimum solution, but we probably get some parameter landscape with several local maxima, and conventional optimization algorithms like gradient-based techniques, for example, Newton's method, tend to get stuck in such local extrema. And then we very probably won't converge automatically to the actual optimum solution. It becomes even worse if we have complicated geometric models. Then we have a high dimensional parameter space with probably a very large number of local maxima or local extrema. And this becomes basically impossible to solve with conventional gradient-based methods. So what people usually do is they use iterative global optimization approaches that don't use gradients. One example would be evolutionary optimization, which is very similar to kind of cultivation processes or natural evolution. That's where the name comes from. So we can draw an analogy, for example, to cultivation of fish. Let's assume that we want to cultivate very large fish. We would probably start with an initial population of some wild fish. We would let them mate, and then we would evaluate their size, their weight, for example. We would just pick the largest of these fish, put them in a new basin, and let them reproduce again. And we would repeat this cycle over and over again. So eventually, after many cycles, where we always select just the biggest fish and let them mate again, we would hopefully come up with some kind of super fish or so. Now, if we apply the same thing to nanophotonics, the fish would correspond to, for example, photonic nanostructures, and we would use some population of random nanostructures, and in some kind of reproduction step, we would mix the geometric parameters of these different nanostructures, and the evaluation process would be then, for example, a numerical simulation. So you already see, if we have like a large population of such nanostructures of, I don't know, 50 or 100 photonic nanostructures, the simulation of all these nanostructures is very probably a quite expensive computational process. And if we need to repeat the cycle, I don't know, maybe 100 times or so, then the entire optimization process here becomes extremely expensive. Last time we actually learned that deep learning is very efficient in solving complicated tasks that we thought before that computers could not solve. For example, it's capable to learn to play Super Mario in a very interesting way. So the question is, maybe we can use deep learning in order to at least accelerate or to turn this inverse design process, which is usually very costly, to turn it less computationally intensive. Okay, so this brings me to the outline of my talk. I will make a very, very short recapitulation of last week's talk for those who haven't been here last week. Then I will dive just directly into how we can use deep learning for inverse design. Specifically, I will talk about the main challenges that occur in inverse design and why it's not directly straightforward to use deep learning for it. And finally, I will try to kind of outline the typical workflow that one would use in order to apply deep learning inverse design to an actual problem by the example of design of a photonic light router. Okay, So very quick recap, artificial neural networks are based on artificial neurons, and artificial neurons are something like a mathematical model of a biological neuron. So we have some mathematical function which has a number of several inputs, and every input here is characterized by a weight parameter, and the neuron itself has additionally a kind of threshold parameter, which is called bias usually. Now we can define the neuron with a step function and say that if the sum of all the input values times the respective weights is larger than the threshold parameter, then the neuron fires. So the output here, the activation is 1. And if it's smaller than the bias parameter, the function is 0. So this would be the step function. However, this is not very practical for actual applications because we want to train the network in an automated way, and this is done, as we will see, using gradient-based methods, and so we need to calculate the gradients. Therefore, the step function is not ideal because it's not differentiable. So it has 0 gradient everywhere and infinite gradient here at the step. So usually people use other functions. One popular one is the logistic function, which is basically a smooth version of the step function. Okay, so now we already have just a very small step to the artificial neural network, which is nothing else than connecting several of these neurons by using their output and feeding it into a next layer of artificial neurons. So like this, we connect several of these artificial neural networks, which gives us neurons, which gives us an artificial neural network. And we see that an artificial neural network is nothing else than a vectorial function, which maps some input vector x onto an output vector y, and which is described by a usually very, very large number of parameters, these weight parameters, w, and the bias parameters of the neurons, b. And now, because we have this very large number of degrees of freedom here, people who use these networks, they assume that it's basically an universal function approximator, and by tuning these weights and bias parameters, we can approximate any possible mathematical function that we would like to approximate. So that's the main assumption, which is underlying deep learning. Now we want to adapt these weights and parameters and bias parameters in order for the network to solve a specific problem, which is defined implicitly by some data, for example, by images, where we want to recognize certain animals or something in the images. This is done by defining first a loss function, and the loss function is basically the error of the network. So this here is the output of the network if you input some input value, and this is the expected output. So we have some training data where we have images, for example, and labels, for example, cats and dogs images, and we have already classified that certain images are cats, others are dogs. Now we feed these into a network and calculate the error of the network if it tries to predict the answer, the type of animal, for example. Now we don't do this on a single data point, but the trick is to do this on a large set of data on a training data set. And the loss function is then the sum over all these errors, or the average error on a large training data when the network tries to predict the known answers. And now this is a function of the parameters of the network, the weights and the bias parameters. And what we do, we will calculate the gradient of this error function here with respect to the weights and bias parameters. And we try to slip down the gradient numerically by changing the weights and bias parameters in order to minimize the loss function. Because if we have minimized the loss function, this means that the network prediction error is minimum, which means that hopefully the network has learned to solve the problem that we have implicitly defined in our training data. So there's a last trick, which is important, that I mentioned last week too, is we also have these local extrema here, which is usually a problem for gradient-based methods, but it's actually in a statistical problem here. It's quite simple to overcome it by not using the entire training data every time we calculate the loss, but just using small, randomly selected portions of the training data, small batches of, I don't know, 50 or 100 images at a time. And then every time we select a new subset of 50 or 100 images, these local extrema will be at different positions or won't be in a local extrema at all. And so we, after doing this a lot of times, we effectively circumvent these local extrema and usually are able to converge to really the global minimum of this loss function. Okay, so very quick recap of the common network architecture. So the most known one is probably the fully connected architecture. It's also called dense or multi-layer perceptron, where neurons are arranged layer-wise, and every neuron of one layer is connected to every neuron of the subsequent layer. Then there are so-called convolutional neural networks, where we don't have to rearrange the input data into one kind of vector of input values, but we can keep, for example, for images, we can keep the two-dimensional character of the images. And what we do now, we define a small array of artificial neurons, which we raster scan over the input data, which might be an image, but it might also be a one-dimensional line of data. And at every position of this raster scan here, we calculate the sum of the activations of the neurons, and we form a new pixel. We use it to calculate a new pixel of the output image of this convolutional operation. And then we repeat this several times, and this will also shrink the dimensionality or the size of the data. Finally, there's a very popular type of networks which allows kind of loops inside the network. For example, effectively this corresponds to connections of neurons far in the network with neurons further in front of the network, or with two connections inside a layer of a network, which are so-called recurrent neural networks. These loops, they form some kind of a memory, and that's why these networks are often used to process sequential data, where we put in one point after the other, one data point after the other, for example, in stock market prices, or in language processing, where we can put in one word after the other, or one letter of a sentence after the other. And there's some kind of memory here, which helps to kind of get the context of a long sequence of information. However, the first and the last architecture here have fundamental limitations. The recurrent neural networks, for example, they don't scale very well with data quantity, because you always need to finish one sequence before you can start the next training step on a subsequent sequence of data. And the fully connected one obviously doesn't scale very well with data dimensions. So if we have a megapixel input image, for example, we have 1 million neurons here, and every one of these will be connected to every neuron of the next one. So there's a tremendously high number of connections, which leads to a huge number of free parameters, which obviously renders the training very difficult. That's why most of modern deep learning architectures are based on so-called convolutional neural networks, or at least there is one convolutional part which is used to downscale the dimensionality of data. And yeah, I went a bit into more detail last week about this, but I will stay here for this. Finally, there are several strategies then for training these networks, or for learning. There's the most common one, most known one, probably supervised learning, which corresponds to a classroom situation, where we have, in the first step, we need to label our data. So for example, we have images of animals, and we look at each image and we say, this image is a cat, this image is a dog, this is a cow. And then we use this labeled data to train our network on the prediction of the labels that we first created for the data. Of course, this requires quite some initial labeling effort. This is also why there's efforts to develop so-called unsupervised learning strategies, which basically work on raw data. One example is a so-called autoencoder, where we define a network which takes as input some data, and the goal is to reproduce the same data at the output. So we don't need to label the data, because the goal of the network is to reproduce the same data. And the goal is to do this by passing through a bottleneck. And actually, such networks start to categorize these data by similarities, for example, similarities in the images. Yeah, so this is quite useful, for example, for automatic label generation already. Finally, there's a so-called reinforcement learning, which is some kind of reward process, which is often used, for example, in robotics, or also Super Mario. If you want a neural network to play Super Mario for you, this would be the method that you would apply for training the neural network. Okay, so far for the quick recap about deep learning. Now I come to the main part of the talk. How can we use deep learning for inverse design, and specifically for inverse design of nano-photonic devices? So inverse design would mean that we have a network where we have as input some kind of desired physical property, for example, scattering efficiency, and the network returns us the geometry or the nano-photonic device that would be required to implement this physical property. So this sounds quite trivial, but in fact it isn't, because these inverse problems are usually non-unique problems, so they are ill-defined problems. And this can be illustrated by a bit off-topic comparison. So let's assume that somebody really likes to drink a lot of beer, like, I don't know, 5 or 10 liters a day. And at some point, this will necessarily lead to an increase in body weight, because so much beer is probably not very healthy. On the other hand, if somebody has someone has some overweight problems, this is not necessarily this does not necessarily mean that he drinks 5 or 10 liters beer a day. It could also mean that he has health problems, that he eats too much pastry, that he is very lazy, or basically can have a huge number of reasons why somebody has overweight problems. So you see that while one direction, drinking a lot of beer, will be directly linked to the consequence of possible overweight, the other way around, the problem can have multiple reasons, and then the problem is obviously not well defined. And this is actually exactly the case what happens in nano-photonic, or in general in inverse design usually. And we can see this already at a very simple example. Let's assume that we want to have a plasmonic nanorod, and the inverse design goal is to get a specific extinction efficiency. So let's assume we want an extinction efficiency of 0.4 or something like this. Then we see here, if we increase the rod length of a gold nanorod, I think I did this at 550 nanometers or so, then we will start to decrease the extinction ratio, and at some point we get at the desired 0.4. But then if we continue increasing the gold rod length here, at some point the extinction will start to rise again and will come again to this 0.4. So we have at least 2 different possibilities here to choose a gold nanorod, which gives us the same extinction efficiency. Actually, and this entire region here has multiple solutions for this inverse problem, and these unique non-unique solutions are responsible for why we cannot directly apply deep learning on this problem. If we would apply the naive approach, so if we would train a network just on a data set where we have some scattering efficiencies and the corresponding geometries, then we would feed here during the training process the target optical property, so the scattering, into the input. The network would predict some required gold rod length, for example, and we would compare this predicted gold rod length to the rod length that we use to simulate the extinction. Now, at some point in the training process, we would show him, for example, 300 nanometer gold rod length, which gives 0.4, and a few training steps later, we would show him 400 nanometer gold rod length, which also gives these 0.4 extinction. So this means that while in the first step, the network was adapting its weights and bias parameters to predict 300 nanometers, a few steps later, it will readapt everything in order for the same input value to predict something totally different. Now, during training, we usually repeat to show the same data over and over again. So this means that the training will actually not be stable. It will oscillate. The generator will constantly change the weights and bias parameters. And finally, it may converge to some totally unphysical mean value of the design parameter, which does not at all give the correct extinction efficiency. So this approach does not work if the inverse problem is not uniquely defined. There are several possibilities to circumvent this one-to-many problem. So yeah, to recapitulate, we have the problem that why the forward problem here is unique. The inverse problem is not unique. So what we can do is, for example, we add some additional helping dimensions, so-called latentless dimensions, to the output of the network, which just serve to distinguish between the different possible solutions for the same inverse problem. So, for example, this would be a very simple scheme of this approach. We would not only predict the rod length here, but we would also predict an extra dimension, which kind of helps to distinguish the different zones where we have non-unique solutions for the problem. However, this is not as straightforward as it's implemented here, but the training is actually quite challenging to stabilize, and you usually need to have some further complicated network architecture. Examples are so-called conditional autoencoders or generative adversarial networks. but they are usually relatively tricky, and the training is not necessarily straightforward to obtain. So you need to play a lot with the network parameters in order to make it work. Then this is why many people use actually a forward neural network. So they train a network on the well-defined forward problem, where you feed some geometry into the network and the network predicts the physics. But instead of in contrast to the simulations, which are usually very slow, the network here, once trained, is very, very fast. So they kind of use the acceleration potential of the deep learning network here in order to accelerate the entire optimization problem of conventional iterative methods. Because usually this evaluation here is really the bottleneck of the procedure. The problem here is, for those who listened last week's, that these neural networks are not very trustworthy, actually. So we never, the neural networks are a total black box. We never know if the neural network actually is stable, if the solution that it predicts for some input value is really correct. We cannot know that, actually. And this is, I explained this last week with these so-called adversarial examples. So in fact, every generative neural network for every neural network, we can find very small perturbations for an input value that turn the output of the neural network into totally incorrect output, but with a very high confidence. So in image classification, for example, we can find a very small perturbation pattern, which we add in a very, very tiny quantity. So we don't even see it. If we have a look at the image, this will look totally the same. But the neural network will completely fail in predicting the image correctly. And this is very dangerous for this kind of global optimization, because this optimization will try to find the global optimum. And if we get stuck into some of these singular points here of the neural network, it will converge to one of these totally wrong solutions, but we have no direct way to check if the solution of the neural network was correct or not. We need to perform, again, additional simulations. And if it's totally incorrect, we need to start over from scratch. And in fact, it might be a totally unstable way of inverse design. So another solution, which is much more robust usually, and also relatively simple to train, is the so-called Tandem neural network. Here we circumvent this one-to-many problem by not comparing the design of the generator with the design that is stored in the training data, but instead of doing this, we first train a simulator network, so a forward network in the first step. So this network here takes the design as input and predicts the physical property. And now in the first step, this will be trained and will be fixed afterwards. And in the second step, we train the generator. And the generator output will be fed then into the simulator, which predicts the physical property. And now we compare not the design, but we compare the predicted physical property of the inverse design with the training data physical property. So with the target, with the inverse design target. And in this way, we are completely rid of the uniqueness of the problem, because we don't care at all about the design anymore, actually. We just care about the physical response of the design. And we compare this physical response to the exact same type of data. So this is a completely unambiguous comparison. And this usually leads to a quite robust training. But of course, the necessary condition is that we have a very accurate forward network here. So if this forward network is not very accurate, the training here is not very robust, and the entire process doesn't work very well. So this just works if we are capable to get a forward network which has a good performance. And another disadvantage of this solution is that we will just get access to one of possibly multiple solutions. So this will converge implicitly to one possible design, which is then enforced during the training process. And if we use the generator after training, it will always return one of the possible solutions. We lose the access to the possible multiple other solutions that could solve the inverse problem. Okay, but these kind of approaches have been very successfully used in the last few years. For example, in the design of metasurfaces, of gratings, of Bragg mirrors, of individual nanostructures, of plasmonic nanostructures. And now this brings me already to the last part of my talk. I will briefly try to explain the common workflow of this inverse design development using a deep neural network by the example of the conception of a nano-photonic light routing device. So our test device will be this kind of MMI. MMI stands for multi-mode interference device, and it's basically a very large waveguide with one or several inputs waveguides and several output channels here. And this is highly multimode because it's very large. Now, if we add at well-defined points here perturbations on this very large waveguide, basically, we get some multiple scattering or some small phase shifts, you can say, that will sum up here in the transmission through the entire channel. And we can control them by positioning them in the correct way so that the full light is, for example, in this 1 to 2 output device here. The entire light is, for example, routed to the bottom output here. By a symmetric opposite design here, we can route, of course, the entire light to the upper channel, but we also can find perturbation patterns which have specific splitting ratios like 30 to 70 or something like this in the output here. So this can be used to design light routing devices. So we wanted to design a more complicated device like this, namely a device with 3 input parameters, 3 input channels and 3 output channels. And this also renders the problem to a multi-objective problem, because we need to define the behavior for input into each of these channels separately. So we need to design at the same time the behavior if we have light input into channel 1 and at the same time light into channel 2 or light into channel 3. So in fact, deep learning is actually quite adequate for this kind of problem because it's already very fast and it's intrinsically multi-objective. And very fast is particularly important because we have a very large design space here, and deep learning is capable to deal with this. We have, in fact, in a very coarse discretization of this volume here, we have already 8 times 44 pixels, which corresponds to approximately 10 to the power 106 possible different patterns. So this is totally impossible to explore in a systematic way. So we need some kind of guided search or some kind of more intelligent approach to search solutions in this huge parameter space. Okay, so we try to apply a tandem neural network on this, and here we start, as I said, by training a forward neural network, which takes as input some design, so basically the pattern, which is not yet shown here, a pattern on the MMI, and it predicts the output for the 3 cases, either input in channel 1, input in channel 2, or input in channel 3. Then the input of this inverse network will be 3 different design targets. The first design target will be which output we get for an input into channel 1. The second design target, which we try to optimize obviously at the same time with this first one, is the output for input into channel 2, and the third one is output for input into channel 3. So here, for example, we would like to have a routing of input channel 1 to output channel 2, input channel 2 to output channel 1, and input 3 should keep guiding to output 3. Now we hope that we can train a network which predicts us some pattern, and this predicted pattern then will be evaluated by the forward network, which we trained in the first step, and which gives us the actual physical response of the device. So for example, here, in case it is successful, this should give us something like a device which routes the lights from 1 to 2, from 2 to 1, and 3 input channel 3 to output channel 3. So we started doing this by generating a large database of totally randomly generated perturbation patterns. However, this didn't work at all. The network just predicted that every possible device has basically 0 transmission, and we noticed that high transmission MMIs are actually very sparse in parameter space. So if you just randomly add some perturbation patterns on the device, this will almost always will lead to light scattering out of the device before the output plane here. So at some points intermediate in the device length here, the light will be scattered outside of the device, and basically no light will arrive at the output. So we could not use totally randomly generated patterns for inverse design. This is why we needed actually a conventional iterative optimization scheme to generate a first data set which contains a sufficient amount of high transmission devices. For this, we implemented a very simple concept. We just added one perturbation at a time at a random position, and we checked if the output increased or decreased, and if it decreased, we neglected this solution and we removed the perturbation again and we added it at a different position. And only if it improved our target splitting ratio, only then we kept the perturbation position and we added a second one. And like this, we built up MMI patterns, and at every added position, we actually stored the simulation. Even if it was worse, we stored the simulation for our data set. And like this, we obtained a large number of very high transmittance devices, but also of devices, intermediate devices, where the transmittance was not yet optimized. And then we used this data set for training of the neural network. However, while this worked more or less, we found that the inverse design network didn't work so well. In particular, often we had some inverse design target, like this one here, where the neural network, the orange prediction here, was very, very good. So the neural network was convinced that this pattern here is a very good MMI to route the light from input channel 2 to output channel 2. But if we simulated this, is the green line, we saw that actually almost no light arrived at output channel 2. And this is because we use this optimized training data set for the training of the neural network. The network kind of assumes that every possible combination of perturbations leads to a very high transmission device, because it didn't, the optimization data set didn't contain any low transmission perturbation patterns. So the network tried to generalize to a new splitting ratio, which it didn't have in the training data, but it assumed that it's possible to put perturbations anywhere at once, and that this will in any case lead to a high transmission of the device, but this is not the case. So it's kind of important also to have some bad examples in the training data, and this is why we use then a so-called some kind of iterative training procedure. So we first generated our optimized initial training data set, then we trained our network on it and our generator, which designed a lot of these not very optimum structures. Then we simulated all these structures again with FDDT, where we found that they are actually not at all as good as the neural network believed. And then we added them to the training data set. So we kept our initial optimum structures and we added all the predictions of the inverse design network that we re-simulated. We added them to the trained data and trained again the network on this extended data set. And this, we repeated this cycle several times, and we found actually that this really improves the accuracy of both the forward network and the inverse design network. And so this iterative training is a really efficient way to resolve this problem that we cannot have all the possible scenario in our initial training data set, or it's very difficult. So like this, kind of the network learns by its own mistakes, and we have some kind of auto-balancing system where the network generates structures that are kind of important for during its generating process, and it learns during this iterative training if these solutions were actually good or if it's actually not worth using them. Okay, finally, this allowed us then to get a network which really worked with a few % error, and it allows, for example, to have manifold designs where we can change. We switch 2 different channels while keeping the third transmission channel the same. So here, for example, the goal was that input channel 1 always guides the light to output channel 3. And we wanted to switch the routing behavior of channel 2 and 3. So here, channel 2 is going to channel 1 and channel 3 to channel 2. And then we have a second design here where 1 goes still to output channel 3, but the input 2 goes now to 2 and the input 3 goes to output 1. And these designs can be found with the inverse design network in about 1 millisecond, whereas a single of these simulations already takes in the order of minutes. So we really have tremendous acceleration, because if we want to use iterative optimization, we need several hundreds or even thousands of calls of this the simulation. So this would be tremendously longer computation time than the inverse design. However, of course, we need this very expensive iterative training data generation here, which also requires a tremendous number of training data simulations. So this is always a balance of if this is useful or not. So if we need to design a large number of different devices, which was basically the goal here, then it's probably, it may make sense. But if we have a single design objective, then maybe it's not the best idea to use deep learning for the inverse design. Okay, so this brings me also to the end of my talk. I want to finish about with a short reflection about, is deep learning always the adequate tool for inverse design, or may there be cases where inverse design can be done more efficiently with other methods? For example, if we have a nanostructure or some nano device which is defined by a very small number of parameters, then I would say that deep learning is not the best approach, because either a systematic analysis is probably more adequate, or we can even apply intuitive design considerations, for example, some antenna equivalencies or so, to better design this, or at least with a much lower effort. Then if we, that's what I already said, if we just want to design a single device or a single nanostructure, for example, for maximum E-field enhancement, then it's probably better to go with conventional iterative global optimization, because otherwise we would need to build up a huge training data set. We probably would need to optimize the training data with some iterative training. And all this is very costly, and also, of course, requires a huge programming and kind of brain input. So conventional iterative optimization is in many cases probably just also quicker. Finally, if we have so this was a paper here where I was also wondering why they were using deep learning. So they basically defined already their optimum device, some photonic crystal with a high Q factor in the center, and then they used the deep learning net and trained it on very small perturbations of this small area here, like nanometer perturbations. And they found that this has an impact between like a factor of 2 on the quality factor. So here I was wondering, I would say you could also do just some random perturbations, what they actually did for the training data generation, and then make a conventional statistical evaluation of the perturbations that you induce in your photonic crystal. Or you could probably even do some intuitive considerations and estimate very roughly how the impact of these perturbations will be on the device. Well, basically the deep learning approach is also some statistical analysis, but like kind of the huge hammer onto a small problem. So I think that thinking a little bit about is this really the best method is always worth it, and often there will be other methods that are probably much easier to employ and will lead to quicker results. Okay, so this brings me to the conclusion, to the summary. I kind of recapitulated what is deep learning and what's the basic concepts in deep learning. Then I tried to explain a little bit the challenges in inverse design by deep learning and how we can approach them. And finally, I explained what specific problems can additionally occur, like this kind of non-optimum or too optimum training data sets, and how we can resolve this if we try to apply it actually on a real problem. Okay, so with this, I would like to thank you, and I'm open for questions. Thanks.